Imagine pulling a rubber band until it feels like a stretched spring, then letting go so it snaps back in an instant. That quick return isn't a Eurostrade T Magica Euros Eda Eurostrade S, the result of microscopic chains inside the rubber that behave like tiny springs. In this lesson we Eurostrade LL uncover how those chains, their random coiling, and chemical links give rubber its surprising elasticity. A rubber band is a thin loop made from elastomer that can stretch easily. When you pull it, the polymer chains inside align along the direction of force. This alignment stores elastic potential energy, which is why the band feels taut. The amount of stretch depends on the materiala Eurostrade S Young's modulus and its thickness. If you release the band, the stored energy drives the chains back to their random coil state. That rapid return gives the familiar snapback motion that many people enjoy. In everyday life, rubber bands hold paper together, secure bundles, or even power simple toys. Their ability to recover shape makes them useful in applications where repeated stretching occurs. However, over time repeated use can cause fatigue and permanent deformation of the polymer. Understanding these mechanics helps engineers design better elastic components for everyday tools. Pause 0.8. Natural rubber is a polymer made primarily of cis-1,4 polyisoprene units. These units repeat along long chains that can slide past one another when stretched. The chains are not isolated. They form a three-dimensional network through crosslinks. Crosslink points act like tiny anchors, holding neighboring chains together in space. When you pull on the rubber band, the chains align and extend along the force direction. The alignment reduces entropy, making the material less random and more ordered. Because of the crosslinks, the chains cannot separate completely. They must return to their original positions. This elastic restoring force pulls the band back once the external tension is removed. The speed at which it snaps back depends on how tightly the network is crosslinked. A higher crosslink density means a stiffer, faster recoil but less stretchability. Pause 0.8. When you pull on a rubber band, its molecules rearrange into a more ordered shape. This ordering reduces the number of possible configurations the polymer can adopt. Because systems naturally seek higher entropy, the chain feels a pushback toward disorder. The restoring force that pulls the band back is called entropic elasticity. It arises not from chemical bonds, but from statistical mechanics of many random coiled chains. Each monomer segment behaves like a tiny spring, and their collective motion generates the macroscopic force. As you stretch further, the chain Eurostrade S entropy decreases more steeply, so the restoring force grows rapidly. The relationship between force and extension follows a characteristic curve that flattens at low strain and rises sharply near full extension. When you release the band, the entropic drive pulls it back to its original coiled state in milliseconds. Thus, rubber Eurostrade S snapback is a direct consequence of entropy maximization in polymer physics. Pause 0.8. Crosslinking introduces covalent bonds between separate polymer chains, creating a three-dimensional network. These chemical bridges, often sulfur atoms in natural rubber, act like tiny hinges that hold the strands together. When you stretch a rubber band, each chain is pulled taut but the crosslinks keep them from sliding apart. Because the network resists separation, the material stores elastic energy as the chains elongate. Upon release, the stored energy drives the chains back to their original coiled state, pulling the whole band together. The strength of this snapback depends on how many crosslinks exist. More links mean a stiffer, less stretchable band. Conversely, an uncrosslinked chain can slide freely and therefore does not recover its shape after deformation. Thus, crosslink density balances flexibility with the ability to return to form, defining rubber's unique elasticity. Pause 0.8. Temperature alters the kinetic energy of polymer chains inside a rubber band. At low temperatures, chain motion slows, making the material stiffer during stretch. When stretched, these rigid chains resist deformation more strongly than at higher heat. Conversely, high temperatures increase thermal agitation, allowing chains to slide past each other easily. This reduced resistance means the band stretches with less force and feels softer. After release, chain mobility determines how quickly stored elastic energy returns. Cool bands recover slowly because their chains are locked into place by limited motion. Warm bands snap back faster as thermal motion helps Euros establish the original conformation. The balance between stiffness and recovery speed is governed by the glass transition temperature. Understanding this relationship explains why rubber behaves differently in a freezer versus a sauna. Thus, temperature controls both how far a band stretches and how quickly it returns. Pause 0.8. When you pull a rubber band, its polymer chains entangle, storing energy like a compressed spring. The stored energy is released when the tension drops, causing the band to snap back toward its original shape. In vehicles, shock absorbers use similar entropic elasticity to damp vibrations while maintaining flexibility. Industrial machinery relies on rubber seals that expand and contract with temperature changes, thanks to the same chain a Euros rearrangement mechanism. Everyday gadgets a Euros from wristbands to elastic cords a Euros use this property to provide quick, reliable tension without permanent deformation. Because the chains return to a higher Euros entropy state, the material resists stretching and recovers efficiently after each cycle. Engineers design rubber components by selecting polymers with optimal chain length and crosslink density for desired stiffness. Temperature variations affect the rate at which chains explore configurations, altering how quickly a band snaps back. Understanding these mechanisms helps in creating safer, longer Euros-lasting products that perform consistently under load. Thus, everyday elasticity is a direct consequence of microscopic chain dynamics governed by thermodynamic principles. Pause 0.8. Rubber bands return to shape because their long polymer chains are randomly coiled. Stretching them reduces entropy, creating a restoring force. Chemical crosslinks bind these chains into a flexible network that keeps the band intact while still allowing motion. Temperature changes chain mobility. A Euros warmer conditions make chains move more freely, speeding recovery, whereas cooler temperatures slow it down.